Good morning. How's everyone doing? What we got in the chat? I don't see anyone yet. It is the day of the test. If you are in the chat, feel free to say hi. It is the day of the test. Who all is here? Let's see. I'm gonna go look at what we got going on. We could do some review. Who wants to review for the test? Jump in the chat and say what you want to review, and we'll start reviewing it. Let's see right here. A lot of sampling distribution stuff. Sampling distributions. Bigger chapter. Important chapter. Important chapter for your knowledge for the test. Sampling distributions. Make sure you've worked it, understand it, and can solve the questions. Got about a third. So big stuff right there. Let's see. Who all is here? Blake, good to see you, Blake. What do you want to do? We could start reviewing some chapters. What do you want to do, Blake? Your call, Blake. You need to put up the taking questions thing. Ask away. Review, but we need some chapter 13/14. Oh, let's do it. Let me get some chapter 13. That was around a third. No, 12 points are interpretations. 12 points should be around 12 points. I think 12 points, like unless there's been small updates. No, chapter 13/14, maybe it's 20 points. I don't know exactly. I don't know exactly, but it's not no, maybe it's 30% because it's 2 chapters. I don't want to say exactly what percent it would be, but the interpretations are, like I said, 12 points. So the interpretations would be 12 points. Those are interpretations. Interpretations. Let's get some review going here. We'll do some review right here. And we will review taking the test. Chapter 13 and 14 review coming up here in a moment. Okay. Let's see. Chapter 13, chapter 14. Okay. Let's take a look. Super nervous now? Well, don't be. Here, let's start off with some review here. You ready? Let's check this out. We're gonna work on this. Let's do it. So let's put in here chapter 13 review. Taking the notes for today. Chapter 13 review. Okay. Good to see you, Lindsay. Thank you so much, Lindsay, for being here. Stat Tool 1, Chapter 13 review. Okay. So Chapter 13, where is Meebot? Oh, he's awake. Let's give him some points. Wake him up. Okay, Chapter 13 is over what? Chapter 13. What is Chapter 13 over? Now, you don't have to memorize what the chapter's over. Ever have that test where they ask you, like, what is the title of the book? We don't do that. We don't do that. So what is chapter 13 over? Like, if you remember, it's the sampling distribution of the sample what? So that can help with your memory to be like, okay, wait, chapter 13 was when we did it with categorical data. It is for proportions, correct. It is the sampling distribution. So what does this mean? Decision trees? Yeah, we could do decision trees next, Victoria. You got it. So what does this mean to say the sampling distribution of the sample proportion? So in this chapter, you know the truth for a population, and you are asking what you might see in a sample. The true, the population can be described with a normal curve, with a mean and standard deviation when 3 conditions are met. We can calculate a z-score for how unusual a sample result is, and p-value right there. Okay. Let's look at each of these ideas and break them down. You know the truth for a population. How is that described in a question? You know the truth for a population. How is that described? Like, if you know the truth for a population, how is that described? The truth for a population when dealing with proportions. So this is the sampling distribution of the sample proportion. So how is the truth for a population described for proportions? I'm asking for the, you know what we're going to do.
Notation, brother.
Looking at sharks? Well, we might be interested in looking at sharks and the percent of sharks that are dangerous. So we could look at the percent of sharks that are dangerous, population being sharks, and what percent of sharks are dangerous. So we'd have to know the true proportion. Now, very close, very close. So because this chapter, so here's what we got to do, and here's the good thing. Good review, Lindsay, right there. We're going to throw some points in a second. So here we go with the points. Since this is proportions, we have to go over here. And let me get it on the screen right here. We need to go to our formula sheet. And we're going to go right here to the formula sheet 2. You can have this printed off for the test or written down. So now we have our formula sheet up and open. With the formula sheet open right here, we go down to proportions and we see the following right here. So if you encounter a question that talks about sampling distribution of sample proportions, anything like that, look right here. Yes. Great job, Lindsay. Great answers. You're right. Then it's P. So in this instance, it's P, but that is also where mu P hat is, which is the expected sample proportion. So then P will usually, but mu's right here. Well, that kind of means more expected, or the mean of the sampling distribution, or the expected sample proportion. So it's a little bit, do we need to show? Yeah, just show it at the start, be like, ayo, and then you'll be good. Because P is categorical too. Great job, Victoria. P is categorical, meaning proportion, true proportion in this instance. So P being proportions. Exactly. Great work. So we could drop this in for some help on the questions. There, Blake dropping some review too. We love it. So here we are with some good notes. So now that we know we're dealing with this chapter, we're going to go here and say the truth for a population is P. The what we might see in a sample is P hat. The z-score of it is the z-score. That is the z-score right here, which is the z-score for P hat. We'd also have to use the truth to figure out how far our sample is away from the truth. We can figure out the parameters of a distribution right here with the normal curve. So normally distributed with mean and standard deviation. Standard deviation being this right here, which is also P times Q over n square root. And the mean of the distribution is where the truth is at. So that's where the mean is at. So that is the answers right there. I guess we could have put mu P out over there. So then Q is the complement of P. Great job right there, Lindsay. So we can do example problems with this. And we also have the 3 conditions. What are the 3 conditions that need to be met in order to describe this as a normal curve? So let's put those 2 things boxed together. 3 conditions, normal curve met. And so what 3 conditions are there? We all know condition 1. Woo! Love some condition 1. Condition 1, random right there. Condition 1 is we have to randomly select the sharks. So we need to know the percent of dangerous sharks to see if our sample corresponds with what we would expect in the truth. Random right there, randomly select some sharks. The sharks we select are less than 10% of the population. Also, the last condition right here is that we have at least 10 expected failures and at least 10 expected successes, or 10 successes, 10 failures, whichever way you want to put it. So we have the 3 conditions for it to be normal. This is the majority of the chapter. The success failure condition, although it requires them to be binary, don't listen to that. The success failure condition states that we need at least 10 successes, at least 10 failures. That is what the success failure condition states. What does the success failure condition state? And I'm being very, very direct with what I'm saying. What does the success failure condition state? What does it state? How would you say the success failure condition is checked? By doing the mathematics of NP, which is sample size times true proportion, sample size times complement of true proportion. You need at least 10 successes, at least 10 failures. That is what it states. Don't go outside those boundaries. Just giving you some hints. At least 10 successes, at least 10 failures. We won't do exactly 10 also, because what if it's exactly 10? I don't know. It's probably all right. There's shades of gray in statistics. It's some people do 5 for it. Some books have said 5, but 10 is safer. Because just to show this really, really, really free, you say, well, why does it matter? It's to say it's approximately normal. Binomial. Here we go. This is what the success failure condition will do, is if you have at least 10 successes, at least 10 failures, then the curve will be approximately normal. If you don't have at least 10 successes, at least 10 failures, then it's not normal. So once again, going back to our notes that we're reviewing right now, by meeting the condition, you can model it with a normal curve. By meeting the condition, you can model it with normal curve. You see here, Roshni and Angel. So if you meet the conditions, you can model it with the normal curve. Some people say it's okay at 5. We like to say, nah, let's do 10. It only becomes more and more normal, and it's perfectly symmetric at 50, and then it is as normal can get because the normal curve is unimodal symmetric. But we like to say it's approximately normal here. So you want there to be at least 10 successes, at least 10 failures, and it's not because the 10% right here. Are there at least 10 successes, at least 10 failures on this curve? Calculate the success failure condition to check it right now and tell me, are there at least 10 successes, at least 10 failures? The answer is down below too. Are there at least 10 successes, at least 10 failures? No. How many successes, how many failures are there? So remember how to calculate and check it, because some questions have you calculate and check the success failure condition. So how many successes, expected successes, how many expected failures? 2 expected successes, 18 expected failures. The formula for the success failure is n times p, which is actually down here, and that is the expected amount. This is the binomial distribution technically, but it's kind of could be an aggregate of the proportions. But it's the best one I have to display the concept of what we're talking about here, about how it becomes more normal as we have at least 10 successes, at least 10 failures. So that's got it. And do not confuse at least 10 successes and at least 10 failures with condition 2, which states what? We're going backwards now. Condition 2 states what? And great job, everybody, answering all these questions, practicing. What does condition 2 state? And then we'll talk about how to check that. And what is the 10? Great job, Lindsay, right there. What does the 10% condition say? So the 10% condition, here I'll write the conditions as people talk about them in the chat. Condition 1 is random. Condition 2 is less than 10%. You can say 10% condition, but if you say less than 10%, you also think less than 10% needs to be sampled. We'll talk about that in a second. And condition 3, we always like to say right here that we pause. Put some pause in the chat if you want. We pause because the third condition is going to be based on the data we're working with. We don't just go straight to it. But no, good job right there, Roshni. We got to throw you some points because it is success failure. It is success failure because we are working with categorical data. Well, I think we'll do chapter 14, then we'll do decision trees next. Thank you for being here. So we pause and we say, what is the variable type? That's not a condition. It's just a pause to ask ourselves, we're working with proportions, so it is success failure. This will hold true when we work through other examples, and you'll see it here in a moment. The success failure condition is we need at least 10 successes, at least 10 failures. So Blake asked us to go out and sample sharks, and it is reported that the true proportion of dangerous sharks is 10%. So Blake has us collect 50 sharks. Do we pass? So here's the notation. You ready? It is reported that the true proportion of dangerous sharks is equal to 10%. The true proportion of not dangerous is thus equal to 90. How did I get 90% right there? So the proportion of dangerous sharks is 10%. According to oceanography.com, they say the true proportion is 10%. What is 0.9? It's the complement. So you just do 1 minus to get with an E. I love that, Blake, right there. It's good stuff. Complement with an E, not with an IE. If you give us typos, we don't care, but I like it. I don't know, because I used to spell it wrong, so there you go. And Blake goes out and collects 50 sharks. He randomly collects the 50 sharks. And great job right there, Lindsay, practicing. We love it. Oh my gosh, I want my 5 to look good. Best 5 ever. So do we pass the 10% condition, yes or no? And how would you describe this to someone? Do we pass the 10% condition? I'll have you do a vote right now. Start a poll, yes or no. Do we pass the 10% condition, yes or no? So take a moment, think it over. Do we pass the 10% condition? And then we'll talk about what it means and why we passed it or not. Ooh, poll's going well. Who can explain why we passed it or not? And what it means? Like, if you know what it means, you'll be like, well, you'll know what to say. I'll give it another few seconds, see what people say. Great work today. People are getting this down. What do people think? So everyone got it right. We have 100% right. The answer is yes. 4 voted. But that's Lindsay, good start. That is the success failure though. So that right there is P, or that's P times Q. What does the 10% condition say? So what does the 10% condition say? And then let's think about how to check it. What does the 10% condition say? So who can tell us what the less than 10% condition means? So it's less than 10%, but what does that mean? And then we'll know how to check it. So what does it mean? There's a formula I often use to check it. I'll show you the formula here in a second. Someone might remember the formula I used to check it. We've shown it in the notes. Well, I added it to the notes to be like, well, theoretically, how would we check it? The less than 10% means what? We sample less than 10% of the what? So we need, think what we sample from. So that's a good thing from chapter 12. What do we sample from? We sample from a what? Starts with a P. We sample from a what? So we want to sample less than 10%. The sample size is less than 10% of the population. Exactly. Exactly right there. So what is the formula I use to check this sometimes? Can anyone remember the formula? I can write things down. I can say them. But when you say them, right or wrong, either way, you're practicing and you're trying to pull the things from your mind. So you're just activating your brain more by you practicing them right now. And if you can remember it, it's like, yes. And then you'll reinforce that memory. Or if you flip through your notes and like, where did I write that down? I'll write it down in about 5 seconds. 5. I'm going to throw 5,000 points. People get it right before Brian can copy his points. 4. Who's going to get it? 3, 2, 1. Oh, we're going 1,000 points right here. Okay. The way to check it is N over capital N. So the 50 great job, Victoria, right there. That is correct. That's what population is. It's capital N. Exactly. Not normally distributed. Capital N is sometimes used for normally distributed. We got to give you those 5,000 points. Getting it right there. So 50 over the population size. So do you think that's less than 10%? Just think theoretically right here. Because you're asking, are the 50 sharks that Blake sampled less than 10% of all sharks? So you could think about the math too, but are the 50 sharks Blake sampled less than 10%? Yeah, that sounds like, yeah, they're probably, I don't think Blake took more than 10% of the sharks in the ocean for his 50 sharks. That's what the 10% condition is. And if you were to estimate the amount of sharks in the ocean, you'd probably say, I don't know, there's probably like 20 million sharks in the ocean. I don't know. Like, maybe I'm just coming up with a number. People are going to be like, how'd you do that? I don't know. 20 million sharks, guesstimate. As long as there's 500 sharks, you're at like more than 500, you're fine. So if you assume there's at least 500 sharks in the ocean, how'd you do that? Also, hello. We are assuming there's at least 501 sharks in the ocean, i.e. we would have sampled less than 10% of all sharks. So under the assumption there are at least 501 sharks, we have sampled with our 50 sharks less than 10% of all sharks. So let's do chapter 14 here briefly and talk about some more concepts. So we're going to do decision trees right after this. And these are just reviews. Do check out the review 2 page. Great review page. So chapter 14. Chapter 14. Here we go. And good to see you here, Evan. I don't know if I said hello. Chapter 14 is what? Sampling distribution of the sample. What? Good to see you here, Lachey. Got some points for all these people being here. What is it for? The sampling distribution of the sample what? Sample mean, which means we're dealing with quantitative data. Now, once again, whenever you see sampling distribution of sample mean, where are you going to go and start looking? You're going to start looking around where? You see sampling distribution of sample mean in a question, you're going to start looking at your where and be like, let me just go out here. Let me do this. We're trained that we know we go over here. We go to that formula sheet and we grab this right here. There's the sampling distribution of the sample mean. So when we know the truth for a population on a quantitative question, there we go. We can describe it with a normal model, or we can describe the expected mean from a sample size n, for a with a normal model with a mean and standard deviation. We can, if the three conditions are met. Oh my gosh. We can also calculate if something is unusual based on how many standard deviations it is away from the expected mean. Okay. So here we go. Could we do, assignment 8? Yeah. We'll just, which question do you want to do in that, Peyton? Let me know which one, and we can do some of that here in just a little bit. Yeah, we might end with that. That'd be good. 2-1 test today, but also 320 has our assignment due tomorrow. So that's some good stuff, Peyton. Tell me which one you want to do in that, which question you want to do, and we'll do that. Let me put it on the notes right here. Thank you, Peyton, for being here. BS 320, assignment 8. Tell me which one. We'll take save us. Okay. Help. Yeah, we're doing later off stars. You bet. Okay. So the truth for a population. What is the true mean? What is the true mean? In chapter 14, what is the true mean? Be very careful. There's just small differences in notation. I really realized when I was teaching this, it really comes down to knowing it's mu. So the truth is mu, and there's also the true standard deviation. So that's true mean, and that's true standard deviation. So those are true mean and true standard deviation, respectively. I did ask for the mean first, so that is the correct answer. So there's the true mean, and there's the true standard deviation, which is, we have to know these quantities. So we're then going to see what happens if we were to know the truth and what is likely in a sample and what is not likely in a sample. The sample mean is known as what in notation? To talk about a sample mean, like something, which is a sample mean. Did I write sample mean on here? Something. Y bar, the Y bar right there is an observed sample mean. So we could say if a sample mean is unusual, that's the something. And y p hat's for proportions. P hat's for proportions. Y bar is sample mean. P hat is for proportions. Y hat is predicted from the regression model. Lots of hats and bars and everything all around. Then last but not least, we have sample size here. Sample size is n. And then standard deviation. So the quantities of the standard deviation and this are normally distributed with a mean of that and a standard deviation of this, but you could also write those quantities. But that's the mean and standard deviation for the normal, and we have to meet the three conditions. Condition 1. What does condition 1 say? What is condition 1? Condition 1 is what? Condition 1 is what? Condition 1 is what? Condition 1 is what? Random. Nope, lowest exam grade doesn't get dropped. No drops on exams, just some assignments. No drops on exams. So the condition 1 is random. Condition 2 is what? So if you go out and the registrar tells you, or Brian reports that historically test 2 has had a 75 average with a standard deviation of 10. The distribution is very left skewed. From the population of 1,400 students who took it this semester, you sample 100 students. Is it unusual if their average grade is 80? And it's 10%. So do we pass the 10% condition here? And how would you know? Good work. And so I was very specific on this one, which this one you can like mathematically check very well. Do we pass the 10% condition? Correct. And great job right there, Evan. Yes, that is the mathematics. So I was very specific. You didn't have to think theoretically, which sometimes if we're sampling from like the US or Tennessee and we say we sample like 20, 30, 40, 50, out of the US, you're like, well, if you sample 100 out of the US, that's less than 10% of the US population. So sometimes it might not be given to you, but you just have to think about it. And great job. We got 30 some points right there. And great job, everyone, practicing. The 10% condition means we sample less than 10% of the population. You might have to think theoretically, like, what is this company making from? If the company says it makes like 8,000 in a day, that would be what they're sampling from for that day. So look for things like population size right here. If it does exist in a question, that is population size. That is sample size. So we sampled 100 out of the 1,400. Now, what do we do? Is that 0.07? It's 1/14th, which is half of 1 cent. Yeah, it is, isn't it? That's interesting. Huh, I bet you the next few digits are that. Sevenths, they're probably like 14ths. Wow, I bet you it's like, yeah, there it is right there. It's cool because of the way it works. It's multiples of 7, so really cool stuff. And then it repeats after that. It's repeating after the 5-7, it's going to go back to 1-4 again. So it's really interesting. Sevenths, it's one of my favorite decimals because of the way it's built on itself. So that's interesting. Cool. I didn't realize that about a 14th, but I should realize it's half of a 7th mathematically. I love math. Math is cool. Says with a dorky laugh. So with this right here, what else do you see notation-wise in this? Well, first off, before we do that, condition 3. Condition 3, I don't know. I take out important stuff and put that in my brain, all the math. What is condition 3? What is condition 3? What is condition 3? Great job, Lachey. Great job, Lachey right there. Lachey, and don't worry, Evan, don't worry. What do you do before you get to condition 3? Before you get to condition 3, what do you do? Put them in the chat. Put them in the chat. You know what to put in the chat here. This is going to be the theme of the remainder of the semester every time before we say condition 3. The quizzes are really tough. That is true. Because it comes down to notation and like it's easier with me walking through it. That's why like I really stress get those hundreds because I do a lot of the work. So this is my advice for the remainder of the semester. Get hundreds on all the quizzes, get 100 on all the homeworks because it's going to be easier like watching me do it and having me explain it. And then if you practice it and you get those hundreds, you're more likely to remember it. But remember, this is the way it goes. If on the quizzes you get like a 70, 75 and with the help videos, then that is the best you're doing with help. Does that make sense? I'm not sure. I hope that's just the way it is. Like if the best you do with help with questions I work through is 75, then the test is going to be a lot harder. Does that make sense? So I don't know where Shelby is. So the test is going to be a lot harder if the best on the quizzes. Oh, Blake was here. So what do you want to get on all the quizzes and the homeworks if possible? Now, please take care of yourself first. Like don't stay up all night doing work. But what do you want to try to get? You want to try to get those hundreds. It's all right if you don't, but start early, ask questions. Let me fix your rounding errors. But you want to get the hundreds because at least then you have some great grades. Like let's say the test doesn't go so perfectly. You still got great grades to back it up. So, my Pearson really has some great questions. There are some great ones. Some of them I'm not the biggest fans of, but there are some really good questions that really test your knowledge, and it comes down to a lot of theory. Evan, that's great. We're throwing you 1,000 points. That's all right. That's great grades. We want that right there. 98's awesome. Strive for the hundreds. You get a 98, you're like, yeah, 98. So strive for the hundreds. It's about what you get out of it. If you like, sometimes I'll explain a whole problem. If you're working with me, that's awesome. If you skip to the end, which they might, can we talk about the test anytime? Yes, you can, Noah. Good question, Noah. You can take it. Yep. Hoping the test doesn't bump my grade down. Well, don't worry. Just keep working along. Because here's what we got to do right now. We got to identify notation. Notation, brother.
Notation, brother.
What do we have right here? What do we have right here? That's going to be important. What do we have? We got to get that notation. And if you're really good, you've already figured out if this is unusual or not. We have mu. Mu is the true mean. Brian reports this as the truth. Sigma is the true standard deviation. That is the true standard deviation. So the mean of the distribution of the sample proportion when the mean is known, mu y bar equals mu. The standard deviation of the sampling distribution of the sample proportion, that's a D. A lot of people can't tell my hand writing because I can't write. There we go. Look at that. I'm going to learn how to spell D eventually. It's the last thing I do. I prefer my old D's. I'll never learn. So sigma over square root of n. And so the new standard deviation, what do you notice? How was Brian nice to himself on this problem? How was I nice to myself? You kidding? There we go. I think Lindsay sees it right here. So is 80 unusual? In a sample, 80 is the y bar, the observed sample mean, and y bar minus mu over standard deviation. Y bar equals. Wait, Lachey, why is it not unusual, or why is it unusual? Be careful. Lachey, I think you're on the right track, but I'm going to pause here and I want people to tell me why it's unusual or why it's not unusual. Zoom out. We are reviewing a test today. We are reviewing the test today. Like, that's all today is right there. I'm going to pause right here. Why is it unusual or why is it not unusual? You're welcome, Evan. Great work. Why is it unusual or why is it not unusual? And then we're doing decision trees next. Let's plug in the numbers and take a look. And Lachey, good question. Is it only one standard deviation? Let's check it out. You ready? So we have the sample mean of 80. We have the expected mean of 75. And the standard deviation of y bar is equal to 1. So it's actually 5 standard deviations above. The most common mistake is not using the new standard deviation. Don't worry, let's share it there. Good work. This is very unusual. The best way to describe this is it unusual if you walk into a room and there's one guy who's, no, Lachey, we're throwing you some 5,000 points. You're here practicing. Think about this. Is it unusual if one guy in a room is 6'3"? Is that unusual? If you walk into a room and one guy is 6'3", is that unusual? If you walk into a room and you'd be like, whoa, there's someone who's 6'3". What in the world? What's going on? Nah, it's not that unusual. It's like, you're kind of tall. But what if you walk into a room and there's 100 people who have an average height of 6'3"? Because that's what we're talking about here is the average. We're not talking about one individual. We're talking about the average. So if you walk into a room and there's 100 guys who have an average height of 6'3", so that means if you averaged up the guys' heights, the guys would have an average of 6'3". You'd be like, well, this is like a kind of tall guy convention. This is like kind of tall. Like, what's going on? This is kind of unusual. This is pretty unusual, right? Because it's not that one guy has that. When we do this chapter right here, we're talking. I'd be. Oh my gosh. That'd be. Oh, I love class. I love class. You can't grow up. That would be lost among that. I'm super short. So we're not talking about one individual being up here at like 6'3". We'd be talking, this isn't 100, but the average for 100 would be over here. If you average together 100 random observations, pretend that's 100, is it likely you would land over here at the top of the curve, basically at 2 standard deviations? Would it be likely or unlikely for 100, pretend it's 100 to be averaged together and then land over here? Think about what would have to happen. You'd have to get a lot of observations over here, which could theoretically happen, but any observation over here would counterbalance it and start to bring it back. This is why this lower distribution is the distribution of the mean of sample size, which has a smaller standard deviation. Can anyone tell me from the original standard deviation how the new standard deviation down here is being calculated? Tell me the mathematics by which we found out the new standard deviation down here is 1. So when I appear, you're going to be missing a very important number to figure out how the new standard deviation for the distribution of the sample mean is calculated. So how would you guys see it right there. How would you calculate it? Standard deviation over square root of n, exactly. So it gets tighter by a factor of square root of n. So when n is larger, which is the two things of the central limit theorem, the central limit theorem states that the distribution will become tighter and also what? The distribution will become tighter, and there's the other part of it. So that is tighter and what? The central limit theorem states that as n increases, both one, the distribution becomes tighter, and two, becomes more normal. And this relates to the third condition, known as the what condition for chapter 14. The third condition for chapter 14, which I might have skipped over, is condition 1 random, condition 2 less than 10%, and condition 3 is what? Just to review, large enough n, which goes towards the nearly normal, which states that we need n to be large enough such that the distribution of the mean is nearly normal. Since this distribution up here is skewed, would a sample size of 2 be large enough such that the new distribution of sample means of size 2 are nearly normal? Will the new distribution of sample means of size 2 be nearly normal? Because is n large enough? Again, n is 2, and this is skewed. So is n large enough? Is n large enough down here? Or right here. Is n large enough? No, it's not. You see how it's still skewed? So we would need, if it's skewed, a sample size of at least what? If it's skewed, you need a sample size of at least what? 20, 25, 20, 20. It's like there's no exact number, and we would generally tell you things on the test like it's skewed or heavily skewed or normal. So if it's skewed, 25. So if I put 20, yeah, and we don't have you write it in. We usually ask theoretically. So 25 right here works. What about now if this is normal? Would a sample size of 2 be large enough such that the new distribution is also normal? Remember, it's just going to get more normal, and this is normal. That's a hint. So if the distribution up here is normal, and then Blake's dropping some good stuff in the chat right there, and those go for respectively normal, skew, very skewed. So the numbers Blake just dropped, 125, 100, are related to normal, skewed, and very skewed. So the more skewed it is, the larger n needs to be. So because this is normal, the new distribution down here is also going to be normal. Because it's just what? The one down here will just be what? It'll just be what normal? Think of the four-letter word. The new distribution is always what normal? The new distribution is always what normal? As n gets larger, the new distribution is just what normal? Four-letter word starts with M. The new distribution down here is just what normal? Four-letter word, meaning more normal. It's more normal. So this one's normal, and this one will just be more normal. Does that make sense? So it's already normal. So if it's more normal, it'll be what? Say it with me. If it's normal to begin with, and it becomes more normal, it'll be what? No, Lindsay, good work. This is the practice. Keep working, Lindsay. You got this. If it's already normal up there and it becomes more normal, then it's still going to be normal. Does that make sense? It was normal, it's more normal, and even with a sample size of 1, because that would be the original distribution. Sample size of 1 is normal, so sample size of 2 is normal. Sample size of 1 is the original distribution. Sample size of 2 is the means of observations of randomly collected observations of size 2. So that'll be normal, and the original was normal. But if you have something ridiculous like this right here, woo, this is super duper skewed. Well, we'll just say it's heavily skewed. So this is extremely skewed, right? What sample size would you suggest to me to make this look more normal? Will a sample size of 2 work? Will a sample size of 5 work? Central limit theorem. Probably about 100. Even if it starts to look like it, it's just hard sometimes to make this. They didn't really plan for me. We'll pretend that still. Oh no, it still got skew. It kind of does actually still have skew. Just wondering, the mean will stay the same, but the standard deviation will shrink. Exactly. The mean will stay the same, and the standard deviation decreases by a factor of square root of n, and that's up here in the formulas. So the mean is going to be the mean no matter what. Like the mean of the sampling distribution is the mean. The standard deviation gets smaller by a factor of square root of n, and the distribution becomes more normal. I think I've heard theoretically that some F distributions or F distributions. I thought I read somewhere one time that very large. Like you can just keep adding more super duper skewed to it. It's just the more skewed it is, the larger n needs to be. Generally speaking, we think of things with not having ridiculous skew. So usually central limit theorem applies for like if it's kind of skewed 25, if it's very skewed 100. What if it's medium skew 50? But like there's no like, does it make sense? It's a gradient. Like the more skewed it is, the larger n needs to be, and that's definitely what the test questions cover about it. So make sure you remember, look at the shape of the distribution. The more skewed it is, the larger n needs to be. Look at your sample size. So what did I imply with this question right here by saying the distribution is left skew? So let's only look at this part of it. The distribution is left skew, and our sample size is 100. Do we pass it? Just the more skewed it is, like if it's extremely skewed, then I don't know, 200. Do you think we pass the large enough n condition right here? It's not, oh, I said very skewed. If we say it's very skewed, what sample size comes to your mind that you need? If I say it said very skewed, do we pass the large enough n condition? And so do we pass it? Is n large enough? Do we have at least 100? Do we pass? Great job. We do. Because if it's very skewed, we need a sample size of at least 100. So we're good on that. 2 seconds here, everybody. We're going to go on quick intermission. Be right back. Hang out. We'll be back here in just a moment. With this We're back. Let's do some decision trees. We still have regression to talk about. So many things. Getting some decision trees up and going. How's everyone doing today? Victoria, Lachey, Evan, Roshni. How is everyone doing? Oh my gosh. My jump license doesn't save. I have no idea why I have to reopen the jump license every time. Need to download Jump 17. You jump every year. Here we go. Well, let's practice. Decision tree time. Okay, well we're gonna practice right here. We got some assignment 8 after this. I'm having a we'll text. Well, we're gonna practice Stat Tool 1 decision tree review. Okay, so when it comes to decision trees, what kind of variables go into decision trees? When it comes to decision trees, what kind of variables go into decision trees? When it comes to decision trees, what kind of variables go in? Kind of, I mean, yes, we put in lots of X's and one Y. That is true. So you want to be like decision trees take, So categoricals with too many levels, like more than 10 levels, we don't use. So let's go make a decision tree with analyze predictive modeling partition right here. Excuse me. And so do you notice things immediately? So this is from your assignment. Do you notice something immediately to be like, hey? Do you notice something immediately like, no, let's not use that? Victoria, perfect answer right there. No identifiers right here. So identifier, no. And so we're going to deselect the identifier. Major has lots of levels. Favorite Starbucks drink. Favorite phone app. There we go. And I think that's it. I think those are the ones. Major has too many levels, definitely. And we could view that, but we're just focusing on the practicing right now. And so we'll remove these right here. That's also an identifier, so we're going to just not use that. So now we have tons of X's. X, and by looking at the colors right here, red and blue can be what or what? Your X's can be what or what? Your X's can be what or what? Red, gender, blue, age. So your X's can be what? Also, your Y can be these too. Rock knows.
It doesn't matter.
So your X's and your Y's can be what? Either cat or quant, which are fine. You don't want categoricals with too many levels. Do I still have the notes up from yesterday? That goes into like the ways in which you can make permutations, and it bogs down the algorithm. It creates overfit models. That's a whole nother story for another day for some 474. So what should we do? Pick a number, any number. Tell me which one we're going to predict today. What number should we do? What number should we do? Pick a number, any number. You pick. Cat quant, we pick it. You say the number. What number? Tell me the number so that way it's easy for me to find. 25. Eliminate the penny. What do you people think? Let's take a vote right now. Should we eliminate the penny? We could do another one coming up here. Should we vote now in the chat? Should we eliminate the penny? And here's what students thought. We had 33% about saying eliminate the penny. And that is the response to the Y variable of interest right there. Victoria says yes. I'm not trying to tell you what I think. I think we should. We used to have a half penny. And nickels. And nickels too. Whoa. Maybe. We used to have a half penny. So, oh man, we need that half penny back. Could you imagine like paying someone in half pennies? Be like, here's my bag of half pennies. It was it Seth Green or someone did a prank or something where they came in and paid in pennies, and that was like 15, 20 years ago. Yeah, there were half pennies. So so times change. So pennies I think cost more to make than they're actually worth. So I keep the mic away. So if it is shown to me that pennies cost more to make than they're worth, I'd say we need to get rid of them. That's my thoughts. Why are we paying for something that's not even worth what it's worth? So actually, the number one deciding factor, the number one variable, and what is the most important split in the tree? What is the most important split in the tree? What is the most important split in the tree? What is the most important split in the tree? The first split kind of, it's like when you leave your house and you're like, I'm going to drive to New York. You're like, do I go north or south on this highway? You're like, the most important turn is going to be your first turn. I mean, the last turn's important too, but you make that wrong turn first and you start heading the wrong way down the road. So the first split right here being gender is the most important split. And if you look, you can actually see inside the tree right here, we have leaf 1, leaf 2. Let's go ahead and pull up the leaf report right here. What does a leaf report show you? And actually, I have a really good drawing of trees. We are covering this in the upper level classes. This is what trees are. So this is we flip the tree. So here's what a tree looks like, at least in the upper level classes as we make them. So you see we have the base or the root of the tree at the start, and then the tree starts to go and become a tree, and then it actually looks like a tree. So the very ends of the trees are called the what? The very end of a tree is called the what? So if you look at this right here, which is how it looks in the upper level classes, we do these concepts too there. It looks like what? Literally yesterday I was like, we last talked about this in 201. Everyone's like, woo, 201. You got those leaves right there. So we call it a leaf report because you would view what's inside the leaves. So you go back over here and there are how many leaves right now? Look at this little tiny shrub, little flower. How many leaves are there currently in this? You can also see the leaves up here. You see them down here. They're the terminal ends of a tree. So how many leaves are there currently? How many leaves are there? It's very important you know it. Great job, Victoria. There are two. There are two leaves. There are two leaves, which are the terminal ends of a tree right there. So when you think about what a leaf report shows you, the leaf report is going to show you, and thank you, Maya, Lindsay, Roshni, excellent work. The leaf report is going to show you what's inside those leaves. So tell me this. What percent of males think we should eliminate the penny? What percent of males think we should eliminate the penny? What percent of males think we should eliminate the penny? Just look at the numbers on the screen and just know how to read this. This is the answer to the why question. This right here is the why question. These are the X's. 50.3% of males think we should eliminate the penny. It's going to get a little more difficult now. Are you ready? Oh, no. Well, that's fine. I'm going to remove age of the earth. Oh, is it text? Redo, relaunch. That just looks so blah. I don't like how long it is. I didn't want a long variable. Okay. 1, 2. Okay. So now, what percent of females think we should eliminate the penny? Ah, great job, Blake, right there. That is true. Blake dropping some knowledge. What percent of females think we should eliminate the penny? So you might have to go look at the tree. And females are all in leaf what? So look at the tree right here and tell me, where are the females? Where did they go? Remember, the leaves go in order. 1, 2, 3, 4. Where are the females at? Where are the females? 1, 2, 3, 4. 1, 2, 3, 4. They are in leaves 3 and 4. You can actually see it up here. You can see gender female, and it's in this and in there. Right here, right here. How many females are there? You can actually find from this pretty quickly how many females there are. So who can tell me how many females? I'm going to put both things on the screen. It might be a little bit small, but I'm going to try to get both on here. And there we go. You can now see the easy way to get how many females. Great job, Victoria, right there. 1056. What is the longer way? And great job right there, Blake, also showing another way of getting it because they're down here. These are the females split apart into 2 groups. What's the super long way, which we'll need to figure out what percent of females think we should eliminate the penny? So down here, remember how you said it's in leaf 3 and 4? In a leaf report, it goes in order by the tree. As in, let's go grab the tree and show it. The tree has, here we go. Boop. Okay, tree has leaf 1, leaf 2, leaf 3, leaf 4. Leaf 1, leaf 2, leaf 3, leaf 4, leaf 1, leaf 2, leaf... Can't write. Oh, that's a lot. 1, 2, 3, 4. So what is the longer way? And Maya's saying it right there. This is literally going to add up to... What will all those numbers down there add up to? You've been typing in the chat, so I'll show it up here. What will all those numbers add up to? What would all those numbers add up to? Exactly. So if you want to know what percent of females should eliminate the penny, think we should eliminate the penny, how could you figure that out? That's the answer to the why question. This is the why question up here. Those are the why answers to the should we eliminate the penny? How would you figure out what percent of females think we should eliminate the penny? What is going to be the math on that? So you know how many females there are, and then just look at the amount that have the why answer. Well, that's how many. Correct, Roshni, that's how many. That is how many. So that's how many. So how would you figure out what percent of females think we should eliminate the penny? You're on the right track. So the answer is going to look like this over this. So if you use my color coding right there, so go ahead, and who's got it? What do people have? That might be the answer. Show me the math. I'll write this right here. And thank you so much for everyone working these questions, because it's one thing for me to say it. Great job, Roshni, right there. Perfect. Roshni, you're getting around some 5,000 points. Keep practicing, keep working these. See if you can solve them, follow along. It's going to create that memory. Like I like to say it this way. I know this is going to be the most obvious answer in the world. I'm not sure that's right now. Is it, check this math right? Oh, it should be a lower number. Lindsay, you're right. I think you might have done, so you might have done the reverse of it. That should be the answer right there. Does that make sense, Lindsay? If you were to watch the greatest pianist in the world play piano, how much would you learn from watching them play piano? Now, I'm not the greatest pianist nor the greatest statistician, but if you were to watch the greatest pianist in the world play piano, plugged in. It's not even plugged. Wait. Is it broken? That's the pedal. Oh, it's not plugged in. It's very important. taking a 1-minute piano break. Do you guys hear it now? Do you hear the piano over here? Yes or no? I never like 2 seconds. All right, some Beethoven. Okay. Okay, break over. I need to play more piano. And I don't like, I got for Elise, of course, for Elise. But I'm in Spam for your piano. Oh, thank you, Abby. Right, Abby, thank you so much. That is very kind of you. I was hoping no one thought we'll make you a mod. I appreciate that. Heart and Soul. Oh yeah, let's play that. Let's just relax for a moment. Let's just relax. Heart and Soul goes dun dun dun. We gotta do one last song here. Curry with fingers a little bit more for smooth play. Gotta do Tiger Claws. One last song right here. Regular piano. One last try. Okay, you should do a Jackson. Well, thank you. Everyone's being so kind. I'm goofing off, and we're being very nice to Brian. I appreciate that. That's very kind of you. Okay, what should we do? Because we got to do some chapter 8. I'm glad, Jackson, thank you for being here, swinging by. I'm glad we could have a little niceties. But thank you so much, everyone. No one's like, Brian, what are you not doing some work? Yeah, we should do more piano in office hours. Maybe we will. I'm just way out of practice, and I like real pianos. This is a nice piano, but I like real pianos. Just saying. We need more cowbell. What kind of questions are there asked about decision trees? You might have to look at a decision tree and understand how a decision tree is made up. Like we do have questions where, like, I can look at the exam. We do have questions about with decision trees and being able to analyze the output. Those questions should be opening. I'm looking at it. I am looking at some questions. The leaf report is going to be the inner part of the tree right here, letting you know what's in each leaf. Being able to understand the leaf report and be able to read it is huge. Knowing how the decision tree is made up of a lot of X's and one Y is very important. Then let's do the R squared. Brian, do you understand what happens if you just cancel the test in different? Yeah. Well, I need to practice. I'm just I don't know. I can't play Pirates today. I'm just, gosh, I think it's all the pressure. Like how many females exactly, like figuring out things like this right here, being able to read it. And then also, let's do a few more. When you have a tree right here, how would that be interpreted? How would R squared be interpreted? We're back on track right now. So please learn the Mandalorian. That'd be cool right there. I was trying to play Corpse Bride and then I couldn't think of it. I'm thinking of Cigarette now by Ben Folds. I don't know why Corpse Bride's out of my head. I can't hear it. I can hear it now. I can. Way out of practice. How is R squared interpreted right there? How is R squared interpreted? How is R squared interpreted? How do we interpret that? Very important for the test. How is R squared interpreted? How is R squared interpreted? Does anyone know? Can you write it out? What are we trying to explain? We're trying to explain variation and eliminating the penny. So that's our goal, is to understand why do people think. Blake, basically, close, very close, Blake. So in a tree, we usually just say the tree at the end of the variables in the tree. And then you write plug in Y and plug in X, but the tree has multiple X's in it. So you might say the X's in the tree. So Blake, pretend this is the test. And so Lindsay, good work right there. Pretend this is the test. And I want you to be like, this is the test. I'm going to get graded on this. I'm going to throw you 5,000 points. I think Evan's done it right there. Evan earning everyone those big 5,000 points right there. Let's read what Evan wrote. 5.9% of the variation in eliminating the penny is explained by the variation of all them X variables. I would count that. If you wrote that, I'd be like, yeah, explain about the variation in those X variables right there. Let's do last bit of interpretations because this is huge. Major stuff. BS 320, we will get back. We will do it. So let's do some interpretations. Thank you for everyone watching. Say hey in the chat. If you're from another class right now and you're just watching this, you had a little bit of fun with the piano. We're about to do Stat 201 regression interpretation right here. So this is regression interpretations. Make sure if you write these out, you're going to get a lot more practice than me just saying them right here. So there will be written interpretations. There will be written interpretations. There will be written interpretations. So let's try to do some right here. Let's try to do some written interpretations. Here we go. Let's predict, and I do like this one. I know we've done it before, but let's do number of pets you own based on yearly pet expense. So we are predicting someone's yearly pet expense based on number of pets someone owns. Now, the first condition, be careful, for doing this sort of analysis is what? The first condition for doing this sort of analysis is what? This is chapter 7/8, regression. This right here is the very start of the test material. The first condition, well, it's not random this time. It's not random. QQ, straight enough, no outliers. QQ, straight enough, no outliers. Plot doesn't thicken. So QQ means both variables are quantitative. So two quantitative variables. Great job there, Victoria, which you have to do regression. Straight enough means a straight line approximates the relationship. Maybe not. No outliers means there's no outliers. Problem there. And plot doesn't thicken means the residual plot, We could also look at the plot, but oftentimes we talk about the residual plot. It doesn't get thicker or thinner. And there's the residual plot. I don't know. A little bit of problems. But we're here to talk about those coefficients. So what is, don't interpret it yet, what is the intercept? What is the intercept? First question is not interpreting. What is the intercept? What is it, man? From Ren Hoek. What is it, man? The intercept, and great job, Jackson. The intercept is 277.09. That is the intercept. So when you're writing this in notation, you can oftentimes go right here and mark it, and do notice it is down there also. So this is y equals b0 plus b1x. So the intercept is b0. The easy way, and write this down, I've written this down a lot, but I want you to write it down right now. Do it, write it down. When x is equal to 0, we expect y to equal b0. When x is equal to 0, we expect y to equal b0. Now, you have to put the context in. So try writing that down, pause the video, write this down, practice it, and interpret it for me right now. Go ahead and interpret it. We've only got like 3 more minutes till I got to send out the class announcement and start the class video. So interpret the intercept. The variables are expensive pets, and pets is the x. Expensive pets is the y. You can see it right there. So when x is equal to 0, we expect y to equal b0, and then comment on if it's logical or not. So what are people going to write? This is the practice. We've done this one a lot. So if you can do stuff like this, that's good signs for the test. When x is equal to 0, we expect y to equal b0. Don't say will, though. Don't say will be this, must be this. We know someone. Don't say no or will. So when x is equal to 0, you just have to plug in what x is. We expect y, you have to plug in what y is. To equal b0, you have to plug in what b0 is. So when someone has 0 pets, we expect their pet expense to be 277.09. You might say that's illogical. You could say, well, it's kind of weird that someone who doesn't have pets. You might say it's illogical because, like, why would someone who doesn't own pets spend money on pets? So Evan, you might have it looks like you might have the slope right there. Exactly there, Blake. I think that'd be great right there. That's a great way of, like, 100%, no greater shake up. Any points for that. Good work right there, Blake. And then Evan, I think, has the slope. So the slope is for each 1 unit increase in x, we expect y to increase by b1 or decrease. I always forget the slope can be negative. For each 1 unit increase in x, we expect y to increase/decrease by b1. So if b1's negative, make sure to say decrease. So how would this be? And think about how it makes sense or doesn't make sense and just talk about it. So for each 1 unit increase in x, try plugging it in as I'm saying it. Try typing it out and plugging it in. For each 1 unit increase, and then type in what x is, we expect y, put in what y is, to increase or decrease. Look at the slope, if it's positive or negative, by, and then put in what b1 is. So for each 1 unit increase in x, look what x is, we expect y, look at what y is, to increase or decrease. I'll highlight them as I'm saying them. For each 1 unit increase in x, we expect y to increase or decrease by b1 on average. Some of them want some average on average. I think you did. Yeah, some graders want on average. Just throw on average on there at the end of that one. Some graders want that. It's not a big deal. No, I think you did. As the number of pets increases by 1, we expect the yearly pet expense to increase by $323.8. Exactly. It's exactly right there. Yeah, for the slope, just throw on average. If you don't get, for my graders, I'll give back the points for that. It's very pedantic. What does this say right here? This is the r squared. So how do we interpret the r squared? The r squared is blank percent of the variation y is explained by the variation in x. So how do you interpret that r squared? Blank percent of the variation in y is explained by the variation in x. So once again, look at your x and your y. The r squared right there is blank percent of the variation in y is explained by the variation in x. Blank percent of the variation in y is explained by the variation in x. Blank, whoops, went the wrong one first. Blank percent of the variation in y is explained for the variation in x, by the variation in x. Great job, Lindsay. Great, Lindsay, 1,000 points, great work. 13.8% of the variation in pet explains explained by the variation in number of pets owned. Exactly. And think about that. There's other variables that would also explain someone's pet expense. Something like, like what kind of pets do you own would also be a source of variation. If someone owns fish versus horses, that's a source of variation that is not included in this model that might explain reasons people spend more or less. So with that, we will be practicing more later. I'm going to make sure we try to do the BAS 320. Sorry about BAS 320. We had to throw in some piano today, some pianissimo. I have no clue. Until then, we're going to start class here in about 7 minutes. Bye for now, everyone. Bye.